Alright, here we have the notes for section 1.2, functions and graphs. So here's our objectives. Identify the domain and the range of a function using this graph or equation. Recognize even and odd functions using equations and graphs. Interpret and find formulas for piecewise defined functions. Write and evaluate compositions of functions. So there in that text box, you've got the lovely definition for a function. A function from a set D to a set R is a rule that assigns every element D to a unique element in R. That must be set. SET of all value or input values D is the domain of the function, and the set of all output values in R is the range of the function. In function notation, we use f of x to denote the range of values that f assigns to the domain value x. The set of all points x, y in the coordinate plane determined by the rule y equals f of x is the graph of the function. The variable x is the independent variable, and the variable y is the dependent variable. Now, for it to be a function, it's here, every element D to a unique element in R. So that means two different x values cannot be assigned. Sorry, reverse that. 1x cannot be assigned two different y values. So you can't have the point 2, 0 and 2, 2. So that's each x value is not assigned a unique y value. That x value 2 has two different y values. All right, so example 1, write a formula that expresses the area of a circle as a function of its radius. So this one is actually maybe something you've memorized. The area of a circle is equal to pi r squared. So find the area of a circle with a radius 2 inches. Area is equal to pi times 2 squared. So the area is equal to 4 pi, which is about, if you want to make it a decimal, 12.57 square inches. All right, so domains and ranges. When a function y of x is defined and the domain is not stated or restricted, the domain is assumed to be the largest set of x values for which the formula give real y values. This is the implied domain. So that means if you don't see anything after it, that's your domain. Now, in some cases, you'll have a restriction like x must be more than 0. That's a relevant domain. So the domains and ranges of many real valued functions of a real variable are intervals or the combination of some intervals. Okay, so the endpoints of an interval make up the boundary and are called boundary points. The remaining points are the interior and called interior points. Closed intervals contain their boundary points, meaning you're using a less than or equal to or a greater than or equal to. Open intervals contain no boundary points, so regular less than, regular greater than. If you remember the open circle and closed circle from plotting on a number line, that's what it's referring to. So example 2, identify the domain and range and then sketch the graph. So we'll actually do that in reverse and sketch the graph. So on my calculator, let's clear this guy out here. See if the scroll up. Shows it pretty well. So 1 over x is our first equation. So 1 over x, draw. So there's our equation. We'll reset the window here. Make it a little bit more obvious. There it goes. All right, so the domain is a set of all x values allowed. The range is all y values. So if you look at this function, it looks like it has a break here at 0. And the sides, as they run off to the left and the right, also don't reach 0. So the domain for this function is values that are not 0. Which actually, if you look at the equation, makes sense. Because if x was 0, you'd be dividing 1 by 0, which you cannot do. The range is y cannot be 0. If you remember looking at the graph, it never reaches the x-axis, so it never takes a 0 value for y. Now, the other way to think about it is if you look at the equation, this is a fraction that has 1 in the numerator. So this fraction can never equal 0 because it's always 1/2, 1/3, 1/4, which is never 0. All right, so the second one, root x, so let's go back to our screen, delete it, the square root of x, oops, and draw it, so it gets this little curve here. So the domain for this, if you look, it never takes any negative values, so the domain is x is greater than or equal to 0. And if you look at the equation, you're taking a square root, which can only be done of 0 or a positive number. You can't take a square root of a negative. The range, if you look, always stays above the 0 value, so y must be greater than or equal to 0. Because square roots always return positive numbers, so it has to be a positive value. 0 is allowed because the square root of 0 is 0. So 3 and 4, example 3 down here, similar problem, use a grapher to identify the domain and range. So the first one, the square root of 4 minus x squared. I need the parentheses here around the 4 minus x squared to make sure all of it stays inside the root. So left a little half circle there. So if you look, the x values are between -2 and +2. The graph doesn't go left or right of that value. And the y values are between 0 and 2. It's the top half of a circle. So the domain are -2 is less than equal, x is less than equal 2. That's how you write x must be between -2 and +2. And the range is 0 is less than equal y is less than equal 2. This is inequality notation. You can also write it like this, which is interval notation, which is a little bit shorter. Brackets for less than or equal to signs. Over here, x to the 2/3. So let's go here. X to the, I've also got to put parentheses around my exponent to make sure the 2 and the 3 stay in the exponent. So that looks like that, little birdie looking shape. So the domain for this one is all real numbers, which is the r with the double back. The range, though, is not all values. If you look at the equation, it always stays above the y-axis, so y must be greater than or equal to 0. So down here we got even odd functions. A function at y equals f of x is an even function if f of -x is equal to f of x. So that means if I use 1, if I plug 1 in and -1 in, I get the same value. An odd function occurs if f of -x is equal to negative f of x. So that if I do the negative value of f of 1, that's the same thing here. So a graph of an even function is symmetric about the y-axis, meaning it's mirrored left to right. It's like a parabola. And that's garbage. Better. Odd function is symmetric about the origin, meaning it's actually mirrored like this. The upper right and the lower left are the same. Okay, example 4. Determine whether the following functions are even, odd, or neither. Now there's a kind of easy way to notate this, so we're going to use x equals 1 for all of these. Oh, I lost my focus, there it goes. So to do that, we're going to do f of 1, f of -1, and negative f of 1. So to get f of 1, I'm going to plug 1 in, so that is 1. To get f of -1, I'm going to plug -1, which is also 1. Now I can stop there, because if these two are the same, I have an even function. So over here, if I do this one, f of 1 is equal to 1, f of -1 is equal to -1. Now negative f of 1, the last option, you don't actually have to calculate anything because it's always the opposite of the first one. So this one is -1. Since these two match, it's an odd function. Now the first and third will never be the same because they are always opposites of each other. So neither would be if none of these are the same. Now the one thing you have to be careful of is you cannot use a number that gives you 0 here on the right hand side, because if there's 0, 0 and -0 are the same, and you may end up with all 3 values being the same. So if you plug your number in and you get 0, you need to choose a different value. So for this one, f of 1 is going to be 1 squared plus 1, so that's 2. F of -1 is -1 squared, which is 1, plus 1, which is 2. So I can stop there. These two are the same, even. Over here, f of 1 is 1 plus 1, or 2. F of -1 is -1 plus 1, or 0. Negative f of 1 is -2, because these two are always opposite. So this is an example of neither. None of it matches, so it's not even or odd. Down here, where I highlighted, that should actually be 0 less than equal x less than equal 1. Okay. So a piecewise function is defined in sections. So this problem is actually going to take us 3 t-tables to do. One for the first equation, one for the middle equation, one for the third equation. So for the first equation, x and y equals -x. The second equation, x and y equals x squared. And for the third equation, x and y equals 1. Now, the values you use, you can't choose any x values you want. You have to look at these restrictions. So for this first one, x must be less than 0. Now, technically speaking, I can't use 0, but I'm going to cheat and use it anyway, because I can fix the problem at the end. And then I need my second x value has to be a number less than 0, so like -1. So if I plug them in, if x is 0, -0 is still 0, and this one would become 1, because it's y equals -x, so -1 is +1. Over here, this one has two endpoints, has to be between 0 and 1, so I'm just going to use 0 and 1. So this 0 squared is 0, 1 squared is 1. Down here, now the last one, x must be more than 1, so I'm going to use 1, I'm going to use 2, the next number more than 1. Now these values actually don't matter because y is always equal to 1, which means this is 1 and that's 1. Alright, now I'm going to do a real bad sketch of the graph. So here's my axes, x and y. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now, when you plot your points, if you used one of the values that is in the inequality, you either have to use an open circle if it's a less than or greater than sign, or a closed circle if it has the or equal to bar. So this 0, 0 value came from that 0, so it's going to be an open circle. Now negative 1, 1, which is right here, didn't come from boundary, so it's just a regular dot. So this section of the graph goes like that, straight out. It doesn't come to the right because it cannot go past that 0 value. It must stay less than 0. So the next one is this one, so 0, 0 again. Now that one's going to be a closed dot, so it's actually just going to fill in the circle there. You're going to have a closed dot at 1, 1 because 1 is also a boundary. So there's that. And the last one, 1, 1, I already got a dot there, and then over to up 1. That's just a regular point, so the graph runs out like that. Because I can use any value more than 1, so this graph continues forever. There's no second endpoint. The only one that is restricted to between 2 points is this middle one, because it has to stay between 0 and 1. This can take any value less than 0, so it just keeps going forever to left. This can take any value more than 1, so it keeps going forever to the right. Alright, so here we got the absolute value function is defined piecewise by that equation. So negative x when x is less than 0 and x when x is greater than or equal to 0. So here it says draw the graph of x minus, the absolute value of x minus 2 minus 1, then find the domain and range. Now I'm going to cheat. These absolute value functions have this general form. The vertex, which if and the absolute value function, that's the point of the v, is located, so then we'll write this down. Vertex is always located at h, comma, k. The a value is the slope of the sides. So in case you forgot, absolute value function is typically a v-shape, so there's your vertex, and the slopes of the sides refers to those things. So this function has its vertex at positive 2, because you notice the equation already has a negative sign, so that negative doesn't count. Now for k, it does. In general rule, the h value is always the opposite of what it appears, and the k value is always exactly what it appears. And this one's going to have a slope of 1. So when I plot this, over 2 and down 1, so there's my vertex. Now if my slope is 1, that means from this point I go up 1 and over 1. So there's one side of the v, and the other side I go up 1 and over 1 the other way. There's my other side of the v. So it says then find the domain and range. So the domain is all reals, because I can use any x value. The range, though, the point of the v is there at negative 1 on the y value, so y must be greater than or equal to negative 1, because I can't go below that value. It can be negative 1, I just can't go less than. Alright, so the last thing for this section is composite functions. So it says, suppose that some of the outputs of a function g can be used as the inputs for a function f. So g and f can be linked to form a new function whose inputs x are inputs of g, outputs, whose function's inputs are x, and the inputs of g whose outputs are the numbers f of g of x. The function f of g of x is the composite. So this is feeding one function into another. So find the formula for f of g of x. If there's the equation for g of x, there's the equation for f of x, and then find f of g of 2. So f of g of x means this equation replaces the x in the f equation. So f of g of x would mean you would do x squared minus 7. If it was g of f, this x minus 7 replaced that x. So here find f of g of 2. So there's two ways to think about it. I can just plug 2 in here. 2 squared minus 7. 4 minus 7 is 3. Negative. The other way to do it is to think about what this does. So what this means is plug 2 into g and get a number. And then take that number and plug it into f. So if I plug 2 into g, So g of 2 is equal to 2 squared, which is 4. And then we take that number and plug it into f. So f of 4 is equal to 4 minus 7, which is negative 3. Same answer we got over here. So this one is f of g of 2 done in one step. This is feeding it from one function to another. And that is the end of this section.